Okay, so here is a problem that I just made up. I have three objects. Object number one is the Earth. Object number two is the moon. Not quite to scale, but really the moon should be further apart and a little bit smaller. But you want to see it. And then I have a spacecraft, also not to scale. And the question is, what is the gravitational force on the spacecraft? Okay, the net gravitational force. That's all I'm going to do is calculate the vector force on this spacecraft. I've already written down some of my constants over here. So I have the mass of the Earth, the radius of the Earth, which you don't actually need, the gravitational constant g, the distance from the Earth to the moon, the radius of the moon, the mass of the moon, and then I picked a location for the Earth. I didn't want to put it at the origin just to make things a little spicy. And then I picked the location of the moon, and I wanted to keep this distance the same. But let's just talk about the calculation here first. So I have this mass right here, this spacecraft. Oh, I didn't put the spacecraft mass. Okay, let's see. Let's go with m spacecraft equals. What do you think? I mean, if it's like a human powered spacecraft, it should probably be. I'm just gonna guess. Let's say it's a satellite, so it's 1,000 kilograms. I don't know. I made that up. Okay. So what's going on here? Well, first of all, there's going to be an interaction between the Earth and the spacecraft. So there's going to be a gravitational force pulling the spacecraft that way. I'll call that F1. There's also going to be a gravitational force between the moon and that spacecraft. I'll call that F2. So the net force, the way gravity works is that I can calculate the individual gravitational force between these two, calculate the individual between these two, and then the total gravitational force will be the vector sum of those. So F total will be F1 plus F2. So how do I calculate F1? Well, let's start with the definition of the gravitational force. F equals negative G m1 m2 r hat over r squared. So the first thing I'm going to need to do is find r. R is this vector. I should have a different color. I have a purple. I don't know if it'll show up. So here's, if I know this is, we'll call this r1 because there's two forces, r1. And to find r1, I have r Earth and r spacecraft. I'll call it rs. So R1 is going to be, if we think about it this way, it's final minus initial. So this is going to be R spacecraft minus R Earth. And so I already gave R Earth. I never gave R spacecraft. We can pick that in just a second. Huh. That's weird. I'll pick it right now. Okay, let you pick it. Pick it. How about you pick R spacecraft is equal to, let's say it's halfway, but it has a same y value as the Earth. So it's going to be halfway. So let's not quite halfway. So I'm just going to say REM over 2. That's the distance from here to there. It's this distance divided by 2, but from here. I know that's weird. Just bear with me. And let's say it has, let's say it's just the radius of the Earth on the y-axis, which I know doesn't make any sense, but it'll be fine. So I do have a value for that. Now the next thing I'm going to do, I need to switch back to blue. I don't know why I'm in purple. So now I have the vector R1. All I'm going to have to do is take R Earth subtracted from this. So I'll take this minus that and just do my normal vector thing. In order to calculate the vector force, though, I'm going to need to calculate the magnitude of R1. So the magnitude of R1 is going to be the square root of R1 x squared plus r1y squared plus 0 squared. I have no z component here. And so in this case, r1x is I'll take rs minus rex, and that'll be my x component. I'll take re minus 2re for the y component, and then square them and add them up. That way I'll find the magnitude. Now what about, I'm going to also need this unit vector, r1 hat. r1 hat is going to be equal to r1, the vector I just found. This is magnitude. That's that. Divided by the magnitude. And why do I need that? Because g is a scalar, m is a scalar, m is a scalar, magnitude squared is a scalar. I need that to make it a vector again. So that's going to say the force on this is going to be in the negative direction as r1, and I use r hat as that vector. So I'm really ready to put everything in and calculate that gravitational force due to this, right? I have everything I need to know, just my values. Let me point down here how I got this. I know that's for the moon. Okay, so that's our F1. That would be F1 equals negative g, mass of the Earth, mass of the spacecraft, r1 hat over r1 vector squared. And yes, I'm going to do this in Python just because it's a good calculator. Now, what about the other force? I'll do this in this red pen, see if that shows up. It did. So one thing I did was I want to use the real distance from the Earth to the moon. And so I want to put this at a realistic position. So if this distance on the x-axis is 1.1 times the radius of the Earth, so it's a little bit off, and it's 2 radius of the Earth up. Well, if I look at this triangle from here to there, I want to put this on the x-axis like that. I know this distance is REM, so that's the distance from the Earth to the moon, which I know. This is 2RE up, and then this is some distance over x. So then I can use the Pythagorean theorem to find that distance, and then just add this distance to get the location of the moon. That's what I did. I kind of wrote that out right here. I know it's kind of messy. But other than that, I'm just going to do the same thing. I'm going to calculate this distance in red, R2. So R2 is going to be our satellite spacecraft minus our moon. That doesn't show up very well. I'll switch back to blue. And then I'm going to have to calculate R2 magnitude. And then I'm going to have to calculate R2 hat. Same way. And then I will get F2 equals negative g, mass of the moon, mass of spacecraft, R2 hat, over the magnitude of R2 squared. Then once I get these two forces, I add them together just like I did up there. Okay, so I'm switching over to Python. I've already entered some numbers, so let's just see what we have right here. I did not include everything. So the first thing, I've already put in some of my values just to get a little heads up jump start. I need to enter in the mass of the spacecraft, ms, is 1,000. I need the location of the spacecraft, which I said was, where did I put that down? Rs equals vector. Okay, I want to treat these as vectors. So I'm going to enter this as a vector. So it's going to be REM, which is a scalar, divided by 2, RE. Be careful with your case, right? Case matters. Now I need to enter in the vector location of the Earth. I'll call it RE. Yeah, that's good. Let's call it R. I called RE up there. Let's just do it lowercase. I know that's bad. RE is going to be vector, just like I wrote on the thing. Radius of the Earth. Actually, it's the radius of the Earth. RE times vector 1.120. And then RM is going to be equal to vector. I should calculate x first. X equals the square root of REM squared minus 4 times RE squared. That's just from the Pythagorean theorem. So now RM is equal to vector 1.1 times RE plus x, and then I put 0, 0. Okay, so first things first, calculate R1. R1 equals, I'm just copying this down straight from my notes here, RS minus RE. If you want to print that out, you can, but you don't have to. I can say print R1 equals R1. And then I should save this. And then run it. So there's R1. But I don't actually need that, so I'm going to delete that. Now I'm going to calculate, actually I don't even need to do anything after that. I'm going to calculate F1. F1 equals negative g times the mass of the Earth, which is me, times the mass of the spacecraft, ms, times the unit vector r1. So unit vectors in Python are built in. Watch this. Print r1 hat equals norm r1. And let's comment out this. Oops, comment. And then run it. So there you see, this is indeed a unit vector with the magnitude 1, right? Because if you do this squared plus that squared, you get 1. So it does work. Okay, so I don't need that. Let's just comment that out. Uncomment this. So that's ms times norm r1. Now I need to divide by r1 magnitude. And again, that's built into Python. So I can say mag r1. Then I have to square it. And let's print this out. Print f1 equals F1 and put the units newtons, and I'll run it. So that's my first force on the spacecraft. It's not huge, you'll notice that, right? Because it's pretty far away from the Earth. Okay, now let's do R2. R2 is going to be equal to RS minus RM. And now I can just go ahead and calculate F2 equals negative g times the mass of the moon, which I'm calling, what do I call it? MM, times ms times norm r2 divided by mag r2 squared. And now we could print that one. F2 equals, in this case, if you're doing it by hand, you can kind of check your numbers here. Now I can find the total force. Ft, let's call it F total, equals F1 plus F2. Now here, you notice F1 and F2 are vectors, so I'm going to get a vector answer there. So I don't need to do anything special. I'll just say add these two vectors. Python knows how to add vectors. Print F total equals F tot newtons. Run. There you go. And now you can do other cool things like change the location of the spacecraft and you'll get a new value. So let's put the spacecraft at, just for fun, let's move it closer to the Earth. So let's make this just REM divided by 5. And you'll notice the gravitational force went up. It's more to the left, right, in the negative x direction because I'm closer to the moon. I mean the Earth, and that's where the Earth is. Where would you have to be in order to get the gravitational force pointing more towards the moon? That's a great question for you to practice, something for you to practice with. But you can change these numbers around. Let me save this. I'm going to give you this code. Earth, moon, force, calc. And I'll post this down in the links below. Okay, we're going to do some more problems with this, but I want to get you used to thinking about gravity as a force and superposition of forces for the gravitational force. But other than that, we're going to do some more problems. So I'll talk to you guys later.